Last lecture we talked about point estimators, and so let's first review what are examples of point estimators. For example, X bar. X bar is a point estimator and usually denotes the sample mean. And another point estimator is an S square. S square is defined to be the summation of square divided by n minus 1, and it is usually an estimator for sample variance. And we know that a very important property of this S square is that this estimator is unbiased. Another estimator can be sigma hat square. So this is also an estimator for variance, and it is defined to be the summation of squares divided by n. However, this estimator is biased, and we have already known that this estimator is the maximum likelihood estimator, right? So even though it does not have the unbiasedness property, it still has some good properties that we will talk about in future chapters. But for now, a more commonly used estimator for variance is still S squared, which is the sum of square divided by n minus 1. And we also talked a little bit about sample median, right? Sample median denoted by X tilde is also an estimator. And examples of parameters. So parameters are fixed but unknown, and they can be mu, right, the population mean, and the sigma squared, population variance. And for example, if we have a Bernoulli random variable with parameter p, then we know that this random variable has a mean equal to p and variance equal to p times 1 minus p. So we can denote as a mu equals p and sigma squares equals p times 1 minus p. And suppose that we have a binomial random variable with parameters n and p. So we know the mean of the binomial random variable is n times p, and the variance of the binomial random variable is np times 1 minus p. So we can denote mu equals np and sigma square equals np times 1 minus p. As we have known that a point estimator of a parameter is a single number, right? It's a single number. And however, this number is unlikely to be the true value of the parameter, because as we know that if we would like to estimate the mu for the whole population, the only thing that we can do is to take a sample, and the sample mean denoted as X bar is almost never likely to be exactly the same as mu, right? So in many cases, it is more useful to get an interval. Okay, so to get an interval instead of just a single number of plausible values of the parameter, and hence the notion of confidence interval. And a confidence interval is always calculated by first selecting a confidence level, and we will talk about confidence level later. And so let's first look at an example. So this example is to measure the average length of a certain species of insects when they mature. So let's denote the average length by mu, and this mu is unknown and fixed, and our interest is to estimate that mu. So how do we estimate that mu? So we take a random sample of 30 insects, and we measure the length of them, and we claim that the average of the 30 sample can be an estimator for the mu. So the measurements are listed as follows. So there are 30 numbers, and after some calculation, we know that the sample mean X bar will be equal to 30.15. So an estimator for mu is 30.15, and we denote that by mu hat. And we know that mu is not equal to mu hat, right? So can we instead give a plausible interval that we can claim covers mu with a certain confidence? So to get an idea about the confidence level, suppose that a fair coin has been tossed. Before seeing the result, okay, you can say that we are 50% sure, or we have the confidence level 50% that the coin lands on tail. Although this indicates uncertainty from the perspective of guesser, there's actually no uncertainty because the coin has already been tossed and it either lands on tail or head. So the confidence level 50% is therefore not about the probability of the outcome at hand. It is a judgment based on the probability of a random outcome. So this paragraph may sound a little bit vague, okay, but we will understand more after we see more of the examples. Now, suppose a population has a normal distribution. So this assumption is very important, okay, because later on we will relax this assumption. But for now, we just suppose the population follows a normal distribution. And we already know what is a normal distribution, right? A normal distribution has mean, mu, and sigma variance label denoted by sigma square, and we write so if x follows a normal distribution, we write x follows n mu sigma square. And when we have n independent random variables, say x1, x2 to xn, and all of them follow normal distribution with mean mu and variance sigma square, then we write x1, x2, xn follows IID normal mu sigma square, where IID means independently identically distributed. And we have also learned that when x1 to xn all follow the same normal distribution, then x bar, which is the sample mean, also follows the normal distribution. And a very nice property of x bar is that x bar is unbiased. So when we say unbiased, it means that the expected value of x bar will be equal to the corresponding parameter mu. And so I'm giving a simple but detailed proof in the lecture notes. So So after talking about the unbiasedness, the mean of the x bar, we talk about the variance of x bar. So the variance of x bar can also be calculated. So the details is also in the accompanying notes. So the variance of x bar will be equal to sigma squared divided by n. And because we already know that when x follows normal distribution mu sigma square, right, then x minus mu divided by sigma will follow a standard normal distribution. So similarly, because our x bar follows a normal distribution with mean mu and variance sigma square divided by n, then we have x bar minus mu divided by sigma divided by square root of n follows normal distribution, standard normal distribution, which means normal distribution with mean 0 and variance 1. And from previous lectures, we also know that when we have a standard normal random variable, then the probability that this standard normal random variable lies between negative 1.96 and 1.96 is 95%. Then similarly, we have that x bar minus the probability that x bar minus mu divided by sigma divided by square root of n lies between negative 1.96 and 1.96 is also 95%. So by rearranging the formula within the probability, we can have the final one, right? We can have this one that is to say that the probability that mu lies within an interval is 95%. So in this case, actually, we are constructing the confidence interval for this mu. right? So the lower bound for this interval is x bar minus 1.96 times sigma divided by square root of n, and the upper bound of this interval is x bar plus 1.96 times sigma divided by square root of n. So as you can see, this interval, right? This interval involves capital X bar, right? So this X bar represents a random variable. So as a result, this interval is a random interval, right? However, if the observed value of the capital X bar is small x bar, such as the 30.15 we have observed in the previous example, then a realized confidence interval, okay, will be a small x bar minus 1.69 times sigma divided by square root of n, and small x bar plus 1.69 times sigma divided by square root of n, where the small x bar is exactly 30.15. So for how do we explain the confidence interval we constructed in Formula 1? So it means that for there are 95% of the chances that this interval will cover the true value mu, and for the rest of the 5% chances the interval does not contain mu. So based on the above considerations, okay, so if x1 all the way to xn is a realized data set of observations, then we say that a confidence interval constructed in this way, okay, is a 95% confidence interval for mu. We also say that this interval, this interval covers mu with 95% confidence. And here are some notes that you need to understand. So basically it says that we have to distinguish the difference between capital X bar and small x bar. So capital X bar stands for a random variable. So when we write in this way, okay, so it means that this is a random interval. So it is a random interval. However, when we use this, okay, when we use this interval, it is a realization of the random interval we just mentioned. Okay, so here this is a realization of the random interval mentioned here. And now, in general, if we would like to construct a 1 minus alpha, okay, so let 1 minus alpha be the desired level of confidence. So if we would like to create a 1 minus alpha confidence interval, then we can construct in the following way. So here it is. So this formula gives us an idea how to construct a confidence level, a confidence interval at any confidence level. Okay, so here mu is our parameter of interest, and this is the lower bound of the confidence interval. This is the upper bound of the confidence interval. So we also in the lecture notes we also derived how this works. Okay, so we can draw. So as you can see in the lecture notes, I drew a PDF for the standard normal random variable, right? So the z sub alpha minus z sub alpha divided by 2 is the quantile, such that the area to the right of z sub alpha over 2 is alpha over 2. Okay, and So by looking at this plot, by looking at the normal plot at the lecture, at the class notes, we know that this standard normal random variable stands between negative z sub alpha over 2 and z sub alpha over 2 with the probability 1 minus alpha. And since we know that x bar minus mu divided by sigma over square root of n is also a standard normal random variable, then we have that the probability x minus mu divided by sigma over square root of n lies between the negative z sub alpha over 2 and z sub alpha over 2 is also 1 minus alpha. Then by rearranging the terms in the probability, we have the resulting formula. So as a result, how do we so here in the box we conclude how to construct a confidence interval for the mean of the normal population. So it is this formula given here. So where the lower bound stands for a realization of the lower bound of the random interval, and the upper bound stands for the a realization of the upper bound of the random interval. Or equivalently, we can write it in a simpler way. Okay, and so this will be a confidence interval. Okay, a confidence interval for mu with confidence level equal to 1 minus alpha. Okay, now let's observe this interval. So we call this value, okay, we call this z as the critical value. And as we recall, what is sigma divided by square root of n? Sigma divided by square root of n is the standard deviation of x bar, right? If you look at our previous notes, or if you just look at the lecture notes that accompanies these lectures, then you will see that sigma divided by square root of n is the standard deviation of x bar. So we also call it a standard error. Okay, we also call it a standard error. So sigma divided by square root of n is called the standard error of the point estimator x bar. So let's look at the insect example again. So suppose that the length of the mature individuals of the species form a normal distribution with parameter mu and sigma square. And suppose that it is known sigma is equal to 3. Then if we would like to construct a 95% confidence interval, okay, it means that alpha will be equal to 5%, right? Then the confidence interval for mu will be given as the point estimator x bar, and this is critical value, and this is sigma, and this is square root of n. So we just plug in every known number into the formula for constructing confidence interval. So, but how do we get this number? How do we get z.025? Okay, so the reason we want this number is that 95% confidence interval means 1 minus alpha will be equal to 95%, right? Which means alpha will be equal to 5%. And when we construct confidence interval, we would like to know alpha, z sub alpha equal to 2. So we would like to know z sub 0.025. So how do we get z sub 0.025? So it means that we would like to find the value, okay, on a standard normal random variable such that the value to the right of this z will be equal to such that the area to the right of this z value will be equal to 0.025, and we label this value as z sub 0.025. Okay, so we would like to find this value, and this value we can find it from calculator. Okay, we can find it from calculator. So this value, so I calculated this value will be 1.96. Okay, and so in this way we found this value, and then we just plug in, then we get this interval. And similarly, if we would like to construct a 99% confidence interval, then it means that my alpha is equal to 1%, right? If my alpha is equal to 1%, then I need to find z sub 0.005, and this value is equal to 2.56. So please make sure that you find it from calculator. Okay, so for the same data, if we would like to construct a 95% confidence interval, then the interval is from approximately 29 to 31. However, if we would like to construct a 99% confidence interval, then that interval ranges from 28 to 31. Now, if you observe these two intervals, what can you discover? Okay, so it shows that the 99% confidence interval is wider than the 95% confidence interval, right? We can also say that the 99% confidence interval covers the 95% confidence interval, right? So why is that? So the reason is that the two critical z values, they are different. So the z value at 0.005 is greater than the z value at 0.025, right? So that makes which makes the 99% confidence interval wider. So now, if we don't look at these two, if we don't look at the numerical values, so let's think about why is the 99% confidence interval wider than 95% confidence interval. Okay, so the reason is that for a 99% confidence interval, right? Because it is 99%, it means that we are more sure. So we are more sure than the 95%, right? So if we would like to be more sure of the confidence interval, then this confidence interval should be wider, right? Should be wider. So that is so if we look at an extreme case, right? So this interval, right? So this interval is very wide. It has infinite length. So this interval will cover mu for 100% confidence, right? So that is to say, when everything is unchanged, the wider your confidence interval is, the more confidence level you will have, right? So that is how we understand the length of these two intervals intuitively. Because we would like a more confidence level for this interval, then of course this interval will be wider in order to cover the true value with higher probability. Now, if we look at how we construct this interval, right? The interval is centered at x bar, where x bar is the sample mean. So that is to say that interval is symmetric around x bar. Then, what is the length of that interval? So the length of the interval is the difference of the upper bound of the interval and the lower bound of the interval, right? So the length will be 2 times the critical value z sub alpha over 2 times sigma divided by square root of m, right? So I explained, so we will look at the length of the interval carefully, and accompanying notes is given in the class notes. So there, the first note is there's a trade-off between the width of a confidence interval and the confidence level. So at at the same sample size n, the higher the confidence level is, the wider the confidence interval is. However, a wider confidence interval has lower precision on the whereabouts of the true value of mu. So how do we understand it? Okay, so it means that when my confidence level, okay, is increasing, it means that alpha is decreasing, right? So when alpha is decreasing, it means that alpha divided by 2 is decreasing, right? So when alpha divided by 2, it decreases. So it means that my critical value is moved a little bit to the right in my plot. Then my z sub alpha divided by 2 will be increasing, right? So if z sub alpha divided by 2 will be increasing, then the length, okay, if this will be increasing, then the whole length will be increasing, right? And as the second point says that if my sample size increases, then the width of the confidence interval decreases. This is because that the sample size n lies in the denominator of the formula, right? So if the denominator increases, then the whole formula will be decreased. So that is to say, if everything keeps the same, like such as the confidence level keep the same, if we have we are able to collect more samples, okay, when that means that n increases, then we will have a shorter confidence interval with the same confidence level, right? So this is a good thing, right? Because we actually increase the precision of the interval estimate. Now here we have another important topic, that is minimum sample size. So given the confidence level 1 minus alpha, in order for the width of the confidence interval in formula 2 to be no greater than a specified value omega, then the sample size n must be at least this. So a detailed derivation is also given in the notes. Okay, so if we would like the confidence, the length of the confidence interval no greater than w, it means that 2 times z times sigma divided by square root of n should be less than w, right? So if we rearrange this formula, then we will have the least sample size. Now, how do we derive a confidence interval? So here is a general situation. So in general, let theta be a parameter whose value is unknown. And we talked about the situation where theta is equal to mu, right? In the following chapters, we will change the theta to sigma square or any other parameter. And let x1 to xn be a random sample. So a confidence interval for theta with confidence level 1 minus alpha consists of two functions that only depend on the observed values of x1 to xn, one called lower confidence limit and the other called the upper confidence limit. And those two confidence limits will satisfy this condition. So that's a general case. This is a general. And in the normal example, we have talked before, one choice of the confidence limit for mu are this and this. So here, this is lower bound, and here this is upper bound. And again, this z stands for critical value. And this sigma divided by square root of n stands for standard error of x bar. As you recall, okay, so the confidence interval we constructed is symmetric, right? Is symmetric around x bar because we constructed using x bar plus minus the same value, z sub alpha over 2. Times sigma square root of n. However, the confidence interval is not unique. Okay, for any alpha 1 and alpha 2 greater than 0 and alpha 1 plus alpha 2 equal to alpha. If we define the lower limit in this way and upper limit in this way, then we still have the mu's, this interval covers mu with 1 minus alpha probability. Okay, and here there are the detailed derivation. Okay, so we just plug in the upper bound, okay, the upper bound in here and the lower bound in here and rearrange it. Rearrange it, we will have this, right? We will have this. And because this is a standard normal random variable, this follows normal random variable, this follows normal, then we can write it as a z. And after we write it as z, then how do we calculate this probability? So it will be the difference of these two probability. And what is this? Okay, what is this? So the probability that so alpha 1. So for example, alpha 1 is here, right? So if this area stands for alpha 1, then this value is z sub alpha 1, right? So the probability that z is less than z sub alpha 1 will just be 1 minus alpha 1, right? It will be just 1 minus alpha 1. And similarly, this will be negative alpha 2. So we know that alpha 1 plus alpha 2 will be 1 or will be equal to alpha. So this formula reduces to 1 minus alpha. So that is to say a lower limit constructed in this way and a upper limit constructed also in this way will also give a confidence interval with 1 minus alpha confidence level for the parameter mu. That is to say, confidence interval is not unique. Okay. However, this confidence interval is not very common. Okay. So usually people use this confidence interval because this one is symmetric, and the best of it is that it gives the shortest length. People like shortest length because the shorter your confidence interval is, the better precision you will have. So far, all of the confidence interval we talked about are based on normal population. Okay, are based on normal population. Now, if we have a random sample from an unknown population, okay, from unknown population, which means that it can be any population such as gamma population, chi-square population, right? We just don't know which one it belongs to. However, we know that the sigma square is known, and we would estimate a constant confidence interval for the parameter mu of this unknown population. Okay, so how can we do it? So here we introduce a theorem which is called central limit theorem. Okay, central limit theorem says that no matter what your original population of X is, okay, then X bar minus mu divided by sigma over square root of n will always approximately follow standard normal distribution. So here x1, x2, xn not necessarily follow normal distribution. Okay, so this central limit theorem tells us even though x1 to xn do not follow normal distribution, after averaging them, okay, after averaging them and standardize this average, we still get an approximate normal distribution. So it means that the probability this standardized, okay, normal distribution that lies between a two critical point will be 1 minus alpha. So consequently, if my observed value of x bar is small x bar, then this is the way we construct a confidence interval for a non-normal population. So if you observe that you will find, right, you will find this confidence interval is exactly the same, right? It's exactly the same as the confidence interval we estimated before, right? So that is to say, when we have large sample, then no matter what your original distribution is, then I can always use this interval. Okay, I can always use this interval as my confidence interval for population mean mu. However, in practice, okay, the population variance sigma is usually unknown. But we need to have an estimate for sigma squared so that we can plug into the confidence interval formula, right? So usually we use this. And this is we know that S is unbiased, right? S is unbiased for sigma squared. So that makes S a good estimator for sigma. So we just plug in S into the sigma. And here's another theorem. So if n is sufficiently large, then this standardized variable where the S is equal to this has approximately standard normal distribution. Okay, approximately standard normal distribution. So this implies that whether or not the population has a normal distribution, then this interval is a large sample interval for mu with confidence level approximately equal to 1 minus alpha. So now let's take a look. The difference between the previous interval is that S is replaced. Okay. So sigma is replaced by S, right? The reason is that sigma is unknown and we have to use S to approximate sigma. And generally speaking, so n greater than 40 will be considered sufficiently large. And since x bar is a point estimator for mu, then the large sample confidence interval will just be point estimator for mu x bar plus minus z, critical value usually denoted by z sub alpha divided by 2, then estimated standard error for mu. So previously, what is standard error? Sorry about that. So previously, okay. So point estimator for mu is x bar, right? So critical z value is z sub alpha divided by 2. So previously we use standard error for mu, right? Standard error for mu, that is sigma divided by square root of n, right? So what is estimated standard error for mu? Estimated standard error for mu is just s divided by square root of n. So now, previously in the insect example, we obtained a confidence interval based on the assumption that the length of the individuals form a normal distribution. However, without that assumption, okay, we still can get an approximate confidence interval for mu, because of the large sample central limit theorem, right? So note that since the sample size is 30 less than 40, the approximation may not be good. However, as an illustration, we still assume that we have the large sample and the central limit theorem works. Now, recall the previous example, we are given sigma equal to 3, right? However, if the sigma equal to 3 not available to us, what can we do in order to solve that problem if sigma is not available to us? Okay, so we can estimate sigma from our data, right, using the sample standard deviation. And after calculation, so how is this calculated? So this is calculated as the this is calculated this way. So where x1 to xn stand for the 30 sample points, okay, in our data, and x bar is their sample mean, which is 30.15, right? So after we calculate this quantity, we are able to get an S, and our S is calculated as 3.823, and we just plug in the formula, right? We plug in the formula and get a 95% confidence interval. So again, this Z sub point this sub point 0.025 will be 1 to 1.96, right? And we also get this value before, right? And plug in, we get 2 confidence intervals. As you can see, still the 99% confidence interval is wider than the 95% confidence interval. Now let's summarize on what we have learned in this lecture. We have learned how to construct a confidence interval for mu when the population is normal, right? So we use x bar minus z, okay, alpha over 2 sigma divided by n, okay, x plus z alpha sub over 2 sigma divided by n, right? And when mu and when it is not normal, okay, we still use this formula if my n is greater than 40, right? Now when my sigma is unknown, right, we use s to replace sigma, where s is equal to the square root of this, right? So for all of the confidence interval we have, so we talk about confidence interval for mu, okay, which is the sample mean. However, for general parameter sigma, so that means sigma may not be equal to mu, right? Sigma can be the theta can be sigma square, right? So for general parameter theta, if theta hat is an approximate point estimator based on the random sample x1 to xn, then typically provided that n is sufficiently large, then this quantity will have a approximately standard normal distribution. Then as a result, this confidence interval is a large sample confidence interval with confidence level equal to 1 minus alpha. Okay, so that is to say, theta may not be mu, right? So what if theta is equal to sigma square? Now, theta hat will be an estimator for sigma square, right? So usually we use s squared to denote the estimator. So that is to say, so this approach for constructing confidence interval is not limited to the population mean mu. Okay, we can also follow that structure to construct confidence interval for any estimator, such as sample variance, okay, such as population variance. So the key point is that first we need to find an estimator. Then we need to find a standard error of that estimator. And if that standard error is not available, then we use an estimated standard error. And some details are also put in the